Conservative versus non-conservative forces. A force is conservative if A, the work it does on a moving object is independent of the path between the object's initial and final positions, and B, if it does no net work on an object moving around a closed path, starting and finishing at the same point. Let's look at this first requirement. When we talked about gravitational potential energy and the work done by the gravitational force, we looked at the motion of this object as it moved from a height h initial to a height h final. We saw a couple of different paths that it could take. It could drop straight down from h initial to h final, or it could move in a curved path from h initial to h final. We looked at the work done by the gravitational force. Work equals the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the two vectors. The force of gravity is equal to the mass of the object times the gravitational acceleration. If the object is dropped straight down, the magnitude of the displacement, s, is equal to h initial minus h final, and the angle theta between these two vectors is 0 degrees. Cosine of 0 degrees is 1, so this becomes our expression for the work done by gravity in this case. If the object moves from h initial to h final along a curved path, the displacement has this length. The direction of the gravitational force is vertically downward, so this would be the angle theta. According to trigonometry, if this is the angle theta, this length is equal to s times the cosine of theta, which is equal to h initial minus h final. So we end up with the same expression for the work done by gravity, whether the path from h initial to h final is straight or curved. Therefore, the gravitational force is a conservative force. A force is conservative if it does no net work on an object moving around a closed path, starting and finishing at the same point. A roller coaster is a good example of a closed path. Let's consider the gravitational force again as the only force doing any work on the roller coaster cars. There are, of course, other forces acting on the cars, but we're examining the gravitational force only to see if it meets this requirement as a conservative force. The gravitational force points downward, so according to our equation for work, as the cars move along the downward parts of the roller coaster, the gravitational force is doing positive work. If you recall, work done on an object by an external force is equal to the change in the kinetic energy of the object. If the work done is positive, that means that the final kinetic energy must be greater than the initial kinetic energy, so the kinetic energy is increasing. It follows then that on the upward parts of the roller coaster, the gravitational force is doing negative work on the cars, and the kinetic energy of the cars is decreasing. Over the entire trip, making one complete loop, the gravitational force does as much positive work as negative work, so that the net work done by the gravitational force is 0. The roller coaster cars have the same kinetic energy at the end of the loop as they did at the beginning of the loop. Since the net work done on the cars by the gravitational force as they move around the closed loop is 0, the gravitational force meets this requirement of a conservative force. If these are the requirements for a force to be considered conservative, then you can imagine that in order to be non-conservative, a force must meet the opposite requirements. A force is non-conservative if the work it does on a moving object depends on the path between the object's initial and final positions. The kinetic frictional force and air resistance are both good examples of non-conservative forces. These forces both do net work on an object in the opposite direction of the object's motion. They also do more work over longer paths. Also, a force is non-conservative if it does non-zero net work on an object moving around a closed path.